You know what I think? I think that you guys are getting coronavirus on purpose. So, just saying, every time something starts happening, quarantines start rising. There's a clear correlation between when I decide to have an exam and when quarantines start to pick up with ferocity. So I think that you guys are having coronavirus parties whenever things start to get tight. So here's what I'm going to do. There are some people who actually have already been, I mean, the word is isolation, I guess. Okay. There was one person that actually was put on 3 different people's close contact list or something. So it was unfortunate. So here's what I did. This is, okay, hang on. What am I doing here? Yeah, all right, here it is. So if you go into assignments, it's going to be the same thing that happened last time. Okay, it's going to be too hard to try to do, to navigate sort of an in-class exam. So what I've done is I've prepared the exam already, and it's actually already in Canvas. You have till Monday to complete it. It's the same game as last time. You can only use the exam itself. There's some helps in there, but don't start working on the exam until you're prepared to not look at your notes ever again, until you're done with the exam, okay? You can't use technology, okay? So that's not allowed other than to get on Canvas and actually upload or download the exam itself, okay? But you cannot use a calculator. There should be no need for it at all, okay? But you should have all of the requisite tools necessary to start working on the exam at any point. But you may want to refresh yourself on some material from the end of chapter 9. And by the way, you should refresh your memory on some specific examples of Maclaurin series that we did, like involving the geometric series, for instance. Like, remember, we did several examples of geometric series that didn't quite look exactly like a geometric series at first. Then we factored stuff out and turned it into a series. And we were able to easily extract things like the radius of convergence and whatnot, yeah? Just based on what we knew about the geometric series. And then also remember, you have tools available to you like integrating and differentiating power series, yes? One of the 2 problems on the exam that have to do with this stuff, I give you a hint. I say, use the last problem, okay? And there should be a clear connection between the problem you just did and the one I'm asking you to do that involves either integrating or differentiating, okay? So so make sure that you remember things like, okay, what's the Maclaurin series for the exponential, for sine, for cosine, for the geometric, and for the logarithm. Those were kind of like the big 5, yeah? Exponential, sine, cosine, logarithm, and the geometric. Everything else was basically kind of gotten at from one of those, okay? So that says due November 9th at 11 a.m. So that's class time, right? So you can go in there. The file's already there. I kind of had to, last night as I was watching various quarantine notifications come in, it just seemed like that's what I was going to have to do. So I did it, okay? All right, any questions on that? Well, here's the deal. I want to work on to work on an intersection problem because I just want to make sure that we're on top of things here. So this example right here, let me just kind of copy this down, and then we'll go over and do some work on in a whiteboard format. So here I have two lines. One of the lines is given by the parametric equations x equal to 1 minus s, y equal to 3 plus 2s, and z equal to 2 plus s, right? You can kind of see that that's what's going on right there in GeoGebra, right? So that's the first line. The second line, okay, the second line in three-dimensional space is given by x equal to 1 plus t. And you might say to yourself, why are you using s in the one line and t in the other? Well, you don't want to like marry inappropriately the place that you happen to be on both lines by kind of using the same parameter on each. You want the 2 points to be able to move freely on both lines. Therefore, you want to use different parameters for each. Does that make sense? You want to be able to move freely on the one line and on the other. Therefore, that necessitates not using t in both places. If I use t in both places, then the points will kind of move together in some kind of rhythmic fashion. Does that make sense? So using two different parameters allows for free movement on both of these lines. So x equal to 1 plus t, y equal to 2 minus t, and z equal to 1 plus 3t, okay? And now what do I want to do? Well, I want to share my screen here. Okay, so I'm gonna go in the whiteboard. Yes. Oh man, it blitzed my thing here. Can someone read that off? It was x equal to, what was it? 1 minus s, y equal to 3 plus 2s, z equal to 2 plus s. Okay, L2, x equal to, was it 1 plus t? And then it was y equal to 2 minus t. And then it was z equal to, yeah, 1 plus 3t. Now, remember, from each of these lines, it's fairly straightforward to actually get a direction vector. So a direction vector for the first line, remember, we get to the parametric equation by taking a point on the line, thought of as a vector, and adding multiples of the direction vector. In this case, that would have been adding s times the direction vector for the line. So by staring at this, you can see right away what a direction vector for this line would be. What is a direction vector for this first line? Remember, it would be s times the direction vector, so that s would distribute to each one of the coordinates. So what's the x coordinate of a direction vector from the first equation in L1? -1, yeah. Now what about the y coordinate for the direction vector? Right, what I'm doing here is I'm thinking of things like, I'm thinking of the vector form of the line. X, Y, Z is equal to x1, y1, z1 plus, I'll use s just to be real pedantic about things, a, b, c, yes? And you know that these parametric equations are gotten at by distributing the parameter and then combining things, yes? So you can immediately extract the direction vector. So the x coordinate would be -1 because there's a -1 sitting right here next to s, yes? What would the y coordinate be? 2. And what would the z coordinate be? 1. Okay. what would the direction vector be for this second line? One, -1, and 3. Okay. So you know that with lines in space, there's like more than 2 options. Before it was either parallel or intersecting, yeah? That's what was happening in the XY plane before, but now it's like you could be parallel, you could be intersecting, or skew, yeah? Remember, skew is the thing where you have the one line kind of going underneath the other one or something, okay? So are these things parallel? Are these things parallel? I don't know, I'm asking you, are they parallel? No, why not? What aren't multiples of each other? The direction vectors are not multiples of each other, yes? Right, so no, because V1 is not a multiple of V2. That's exactly right. Okay, if V1 was going to be a multiple of V2, just by looking at the x coordinate, you could say, oh, it's -1 times V2 or something, yes? Yeah, but then that doesn't work in the other coordinates, okay? So they are not parallel, no. Okay? So what's the next question? And by the way, you should proceed in this way. Determining parallelism is very easy. You just look at the direction vectors, you see if the one direction vector is a multiple of the other. Then you say, okay, well, are they intersecting? Okay? Are they intersecting? Okay, well, that's sort of an interesting question. And by the way, if we discover that they don't intersect, what do we conclude immediately? Skew, the only other option, yeah? So we've already ruled out parallel. Now we've moved down to, are they intersecting? If we answer that in the positive, then they're intersecting, obviously. If we answer that in the negative, then we know what has to be true about these lines, namely they're skew, okay? So are they intersecting? Well, the way that you do this is kind of interesting, all right? What you do is you take the x coordinates and you set them equal to each other, okay? So if I set x equal to x, then I know that 1 minus s would have to be equal to 1 plus t. Does that make sense? This is another reason that you don't use the same letter, okay? Because this is saying the x coordinates have to be the same for some value of the parameter in the one line and some other value of the parameter in the other line, yes? It doesn't have to happen at the same value of the parameter for both. It could happen, you know, like s could be one thing and t could be another, and it makes the x coordinates the same for these two lines. So I get 1 minus s is equal to 1 plus t. If you would have used t in both places, you would have made a massive error. What you would have done is you would have said 1 minus t equals 1 plus t. Hey, I know how to solve that. T is like 0. And then you would have plugged it in and said, oh yeah, okay, it looks like things are going to work out here pretty nicely. That's not how it works. The parameters allow you to move freely on both lines because they're not the same. So there could be one value of the parameter that makes my x coordinate the same as a different value of the parameter on the other one, yeah? Okay. Then what you do is you say, all right, not only do I want x to be equal to x, but I want y to be equal to y, okay? And if I set the y coordinates equal, I get that, 3 plus 2s would have to be equal to 2 minus t. Don't you see? Yeah? Okay. And at this point, I really have 2 equations and 2 unknowns. Know what I mean? I have 2 equations and 2 unknowns. So I can literally figure out what the value of s and t would have to be to make this happen. saying, okay, I have to make the X and the Y coordinates the same. I have two equations and two unknowns. I know I have not talked about Z yet, but that's okay. I don't need to. Okay. I can now figure out what S and T would have to be in order to make this work. Okay. And in this case, it actually works out kind of nice. If you add these two equations together, I mean, you guys know what to do. You could like solve one equation for T and plug it into the other one. There are lots of like little algebraic ways you could do this. Yes. It's like a high school algebra problem. But one thing that you can do is you could add these equations together. And what would I get if I add these two equations together? What would I get on the right? You guys realize why I would want to do that. Look what happens to the T's, right? What do I get on the right-hand side if I do that? 3. And what do I get on the left-hand side? 4 plus S. So what does that tell us S has to be, for crying out loud? S would have to be -1. That's nice. Okay. So in order for this to happen, S would have to be -1. And now I can figure out what T is. It doesn't really matter. I mean, I can put it into either one of these equations. Okay. So for instance, if I put it into this equation, I would get 1 minus S. Oh, oops. What am I doing here? For crying out loud. I know what S is. What 1 minus what? -1 would be equal to 1 plus T, which means 2 is equal to 1 plus T, which means what? T would be 1. Right, and I could have also plugged in S equal to -1 into the second equation. I mean, just to convince you of that. I mean, I think you probably are convinced, but you know, you go 3 plus 2 times -1 would have to be 2 minus T. So you would get 3 minus 2, which is 1, equals 2 minus T. And of course, that means T is 1. Yeah? Okay. So T would be 1. Which we already knew. Okay? So what we have just found out is in order to make the X coordinates the same and the Y coordinates the same, there's exactly one way for that to happen. S would have to be -1 and T would have to be 1. Yeah? Okay? S would have to be -1 and T would have to be 1. Let's just sort of check this, check to make sure that this is working for X and Y. You know, sometimes it's hard to believe. So for L1, okay, if I plug in, so what was the parameter there? S is apparently -1. I would get X equal to, think about it, if I plug in S equal to -1, X would be 2, and what would Y be? If I plug in -1, what's Y? 1. And now I can actually figure out what Z is as well. If I plug in S equal to -1, Z is 2 plus S, right? If I plug in S equal to -1, Z is 1, yeah? So we're at the point 2, 1, 1 on the first line. On the second line, I plug in the parameter T equal to 1. I get X equals, I'd better get X equal to 2. Is that what I get? Sure. Okay. I'd better get Y equal to 1. After all, we did algebra to force that issue. But what about Z? What's Z? 4. That's not good. Well, I don't know. You know, like these aren't equal to each other. Yeah? So what does that tell us about these lines? Think about it. We said the only way that these lines are going to intersect is if the X coordinates are the same and the Y coordinates are the same. That forced what the parameter values were. We saw that indeed it made the X and the Y coordinates the same, yeah? But then it failed to make the Y coordinates the same. So what does that tell us about, these lines? So L1 and L2 are, do they intersect? No, they don't. They are Skew. Okay? L1 and L2 are skew. We did everything we could to try to find a point of intersection, and we failed. Yeah, we figured out what the parameter values would have to be, and it turns out that that did not work. Okay, which is kind of interesting. Okay, so any questions on that? That's how you go about kind of going from, are they parallel? Yes or no? If no, are they intersecting? Yes or no? If no, then you immediately conclude that the lines are skewed. I just wanted to show you, I wanted to show you this picture. Here are the two lines like graphed in GeoGebra, right? Here's the first one, here's the second one right here. Notice this point right here, where does that look like that is in X and Y? Think about it. See this point right here where it looks like they're crossing? We're literally above the lines right now. Do you see what I'm saying? See this? There's the Z-axis. The X and the Y are the red and the green axes respectively. Do you see that it looks like there's an intersection point right there? As we're hovering above these lines, we're like, whoop, hovering up here. Okay, we kind of see that point. What does it look like that point is in its X and Y coordinates? What does it look like the X coordinate is? 2, and the Y coordinate looks like it's 1, like we said. But then if I kind of pull this into the third dimension, look what happens. Do you see? Those points which look like the same point when I was looking down from it from a bird's eye view from above, it's not the same point at all. In fact, the Z coordinate of this one is 1, and the Z coordinate of this one is 4. Yeah? So indeed, these lines are skew. Look at that. See them? They're kind of skew like that. Yeah, that's sort of interesting. So there's our skew lines right there. I think that's kind of interesting. Any questions on that? Those are not parallel. They're not parallel and they're not intersecting. Yeah. But if you hover above it, it looks like you have an intersecting point. By the way, I could have done the same thing in like Y and Z. Like I could find out the place where these things look like they, oops, I'm getting really picky here. Yeah, I could actually figure out where it is that these guys intersect, which looks like right here in Y and Z. Does that make sense? But then I would be sad to discover that I can make the Y and Z coordinates the same, but once I do that, what about the X's? Not the same. Yeah. So I would fail to make that the same, right? Because the X coordinates would not end up being the same for those Y and Z coordinates that make to have the Y and Z coordinates match up. Okay. And you could do the same thing over here as well, just so you know. Okay. Oh man, I'm getting real picky here. I could go with X and Z. I could figure out what this point was right here. Yeah. But then I would be sad to discover that the Y coordinates weren't the same. Yeah. Okay. Just wanted to point that out. That's kind of a neat little, thing that's different from what we were able to do in two-dimensional space for sure. Okay. All right. So we have one more thing to do in section 5, and that is computing the distance between a point and a line in space. A point and a line in space, okay? So last time we sort of, we set this up and came up with a formula, which was this, if you'll recall. It made sense to us though, because, let's see, did I have the picture in here somewhere? Maybe not. I don't think I had the picture. Let me draw the picture again just so we see this. This is a point and a line. Okay, so here's this line right here. Here's a point that I'm going to call Q. I want the distance from the line to this point. And you know that if you have a line, then what do you have? You have a point, P, and you have a direction vector. And we'll call that U because that's what the book decided to arbitrarily change to all of a sudden in this application, okay? And we have a direction vector u. So I don't know, we have this point P, we have a direction vector that we think of as kind of emanating from P, just out of convenience. Okay, so let's call this vector u. And then we form the vector PQ. Okay, so here's PQ vector. I think about this angle theta between PQ and U. And then the way to actually figure out the distance from this point down to the line, okay, so this is the distance D, is to use trigonometry, yes? We simply use trigonometry. And what trigonometric function would we use in this particular case? I want this side over here, yeah? I want this opposite side over here, opposite side. Yeah, so I would use what? Sine. I know that sine of theta is equal to D, the opposite side, over what? I think I just saw something. Oh, sine. Oh, he said sine. Great. Looked like sin. We'll let that one go. It's great. Okay, so sine of theta is equal to D over what? Length of PQ, that's exactly right. So in other words, D is equal to, D is equal to length of PQ, sine of theta, sin of theta. Yeah? So why is that the same as this equation over here? Well, it's because we multiply and divide by the length of u, just out of convenience, okay? If we multiply and divide this thing by the length of u, we get the length of PQ times the length of u times sine of theta over the length of u. And then we remember length of PQ, length of u, sine of theta, that's just the length of PQ cross u, yeah? So that's where this formula actually comes from right here. Okay, so we have that nice little formula that pops out. Okay, so if I want the distance between a line and a point, that is the formula that we are going to use. Okay, that's the formula that we are going to use. Okay, let's do a little example, and then we'll kind of move on from here. Okay. Any questions on this before we start utilizing this formula? I know that we did this last time. I just wanted to make sure that I wasn't rushing too quickly at the end. But any questions on this? All right, so let's, oops, what's happening here? Let's do an example, okay? So can someone read off that those two lines? But again, I should remember them, but I don't. So L1 was x equal to 1 minus s, y equal to 3 plus 2s, z equal to 2 plus s, okay, and L2 was x equal to 1 plus t, y equal to 2 minus t, z equal to 3 plus t. Oh, oops, 1 plus 3t. Okay. So let's compute let's get a point on L1. So is there a point Q on L1 that is fairly obvious? 1, 3, 2. That's just gotten out by taking s equal to 0. And we get Q equal to 1, 3, 2. Okay, so what's the distance D from Q to L2? Well, remember, we had a direction vector for this second line before. We'll use U just so that we can see the formula clearly in play. What is the direction vector for the second line? What's the direction vector for the second line? One negative 1, 3. Right, you basically just do the coefficients of the parameter, yeah? Okay, so I have the direction vector. So L2 has direction vector U equal to 1, negative 1, 3. Okay, what about a point P on L2? Okay, well, what could I do here? Take what? What's an easy parameter value to plug into L2? Yeah, 0. So take T equal to 0. And so P is, okay, we could have done anything we wanted, but let's just keep it simple. If I take T equal to 0, I get P equal to 1, 2, 1. Okay. So D is going to be equal to the length of PQ, the vector PQ crossed with U, divided by the length of U. Okay. So what is PQ? Okay, so PQ, right? To compute PQ, I would have to go terminal minus initial, right? So here's Q, here's P, and I would go Q minus P. So what's the first coordinate when I go, when I look at the difference in X coordinates? That's 0. Okay. What about the second coordinates? 3 minus 2 is 1, and 2 minus 1 is 1. And I have to cross this thing with 1, negative 1, 3. Okay. And it's the length of that divided by the length of U. Now I can compute the length of U pretty quickly, can't I? That's just going to be 1 squared plus 1 squared plus 3 squared, square root, yes? So it's the square root of 11. Okay, so what about the cross product? What about that cross product? Let's just go on up here and I'll do a little IJK matrix. Okay. Does it really matter whether I do the cross product in the one order or the other if I'm just computing the length of this thing? Does that really? No, right? It doesn't matter. All that flipping the cross product around will do is to flip the vector around, but the length is still the same. It's always the area of the parallelogram determined by those two vectors, remember? Okay, so I'm going to go 0, 1, 1, and then 1, minus 1, 3. Okay, so I want the determinant of that. Okay, remember I cross out the first column and I go 1 times 3 minus negative 3 times 1. Yes. Oh, sorry. Thank you. This should be what? Say again here. Yeah, negative 1. Oh, thank you. Yes. Okay, so you cross out the first column and the first row, and you go 1 times 3 minus negative 1 times 1. Yes, remember that? So what's the first coordinate going to be? 3 minus negative 1 is 4. Okay, the second coordinate, you always remember you have to slap a minus sign on here, yeah? You cross out the second row, or the second column in the first row, and you go 0 times 3 minus 1 times 1. So it's going to be negative -1. Yeah? Comma. What is the third coordinate going to be? Well, you cross out the third column in the first row. It's going to be 0 times -1 minus 1 times 1. So it's -1. Okay? So we get 4, 1, minus 1. Okay? So what is, we're almost done here. So what is the length of the cross product then? Square root of 18. Okay, square root of 18. On the bottom, I have square root of 11. Of course, there's not much I can do here by way of simplification, yes? The answer here for the distance from that point to that line is just, I could put it all under the same square root, I guess. Square root of 18 over 11, yeah? Any questions on that? I think that's kind of fun. Now, does that mean, because remember we had these two lines that were skew, correct? You could ask about the distance between those. You could ask about the distance between those two lines if you really wanted to. Is that the distance between those two lines though? The answer is no, because I just picked a random point on the first line and I kind of computed the distance from that point to the other line. That's not in general going to be the distance between the two skew lines, okay? To figure that out, what you would have to do is something like what we did before. You would kind of have to get it to a point where they were kind of crossing over each other, either in the YZ plane or the XZ plane or the XZ plane or the XY plane. And then what you would have to do is kind of take that point and compute the distance from that point to the other one, okay? So that gets a little bit trickier, but you know, we just picked a point on the line, computed the distance over to the other line. But I just want to warn you that that is not in general going to be the distance between the two lines. Okay. Yeah. All right. Any questions on that little computation? All right. Well, I want to move on to the next section, which is on surfaces in space. Okay, surfaces in space. 11.6. So this is going to be kind of an extension of what we did with conic sections. All of the conic section stuff, remember, what were the three main conic sections we discussed? You remember? Parabolas, ellipses, and hyperbolas, yes? And of course, circles fell under the category of ellipses, yeah? Now we're going to talk about sort of like three-dimensional versions of those sorts of things, yes? Okay. We're going to talk about something called cylindrical surfaces, quadric surfaces, and then we're going to revisit yet again how one can actually get surfaces of revolution in three-dimensional space, okay? There's a whole class of surfaces that we can get in three-dimensional space by revolving curves in certain ways, okay? The quadric surfaces stuff is I think, probably the most interesting of these three topics. But let's first talk about cylindrical surfaces, okay? First of all, before we get going, this was the equation of a sphere, yes? Then we had the equation of a plane, given by that. And by the way, x0, y0, z0 was the center of the sphere in the first equation, and r was the radius. In the second thing, the plane equation, what relevance was a, b, c, the coefficients of x, y, and z? What was that? You remember? What about those coefficients? That's the normal vector. The normal vector. This is the vector that would be perpendicular. Yeah, Ricky said it. There you go, Ricky. All right. Okay. ABC, like that. So here's the plane, right? And we have a normal vector, which happens to be perpendicular to the plane. Okay. Right. So the coefficients of of x, y, and z respectively form a normal vector for the plane. Okay. All right. Here's a question I have for you. What do we get if we move a vertical line around the circle? I'm trying not to use r squared because r squared might remind you too much of polar coordinates, okay? What do you get if we move a vertical line around a circle, x squared plus y squared equal to a squared, where a is a fixed positive number? What are you going to get? Yeah. Right, so you're going to get a giant tube, yeah? A cylindrical tube, right? Ricky said a cylinder, yes. It's going to be a circular cylinder with the z-axis right in the middle, yeah? Because x squared plus y squared equal a squared would have been a circle in the xy plane of radius a. But now we're letting z be anything over that circle, and that kind of stretches that thing out into a cylinder, yeah? An infinite cylinder. All right, so it looks like this. So there's the circle, x squared plus y squared equal to a squared down in the xy plane. And then if we let z be free over that circle, right? Z doesn't appear, so it's free to do whatever it wants. But x and y are kind of restricting what points actually get sketched out in the surface, yes? But you get something like this. We'll talk about what that word rulings mean in just a minute. It doesn't have anything to do with like judicial decisions or anything, yes? There's actually a technical mathematical term, rulings, that we're going to talk about here. By the way, a cylinder, this is called a right circular cylinder because it technically is still a cylinder even if I had a bunch of tilted lines, okay? If I had a bunch of tilted lines that were all parallel to each other, you would still call that a cylinder. And even more loosely, even if that thing wasn't a circle down in the XY plane, even if it was some crazy curve and you had a bunch of lines that were parallel, you would still call that a cylinder, which is kind of weird, okay? Okay, so let's talk about that. So here is the definition of a cylinder. Let C be a curve in a plane, and let L be a line not in a parallel plane. Okay, so you know, C could be any curve at all, right? And I'll kind of draw a picture here in just a minute. The set of all lines parallel to L that intersect C is a cylinder. That's a very, very loose definition. Technically speaking, that definition actually includes things like a plane. Do you know what I'm saying? Because the curve could have just been a line in like the XY plane. And all of the lines could have just been kind of coming in diagonally through that given line, and that would give us a plane. Do you see what I mean? Okay. Okay, the curve C is called the generating curve. Okay, so sort of the curve C is called the generating curve or the directrix of the cylinder. And the parallel lines are called rulings. Rulings, okay? So what are the directrix, or what's the directrix of this right circular right circular cylinder? What is the directrix? That has to be the curve that all of the lines are kind of following. So the directrix in this case would just be the circle. Yeah, the circle would be the directrix. Okay, so that's the directrix. What are the rulings? Well, the rulings are lines that happen to be parallel to the z-axis in this case, yes? So the directrix are all these lines. By the way, I only drew a few of them. There's actually infinitely many of them, right? So all of those are parallel to each other, and in particular, they're parallel to the z-axis, and they happen to go through this generating curve, the directrix, which happens to be the circle. Okay? Any questions on that? So the rulings are the collection, that's the collection of parallel lines that go through the curve. Okay? Any questions on that? So here, let me actually draw another picture. So like I could have a situation like this. I might have, you know, I might have some crazy curve. I don't know, something like this. Okay. And so that might be my directrix. Okay. And the rulings, I mean, I just have to start with one line that happens to intersect this thing. Okay, so that would be one line, and then all the other lines would have to follow suit. Okay, so there would be one, there would be one. Do you see what this thing would kind of look like? Yes, it would look kind of like a plane that's been bent up or something like that. Yes, so this curve C, okay. This curve C is the directrix, and these guys, okay, these guys right here, these are the rulings. These are the rulings. And you can see that you're going to get a surface in three-dimensional space when you do that. And that is called a cylinder. It's like a generalized cylinder. Does that make sense? It includes the cylinders that you're used to thinking about. The right circular cylinders. Okay, but it's much broader than perhaps you realized. So could you have a cardioid directrix? Yeah, sure. You could have a cardioid directrix, right? And then you would have some cool looking, three-dimensional thing, some three-dimensional heart kind of going up and down forever or something, yes? So that's cool. You could have a directrix curve that's anything at all. Yeah. Not necessarily. That's not something that's specified here. So the directrix curve does not need to be closed. It doesn't need to start where it finished necessarily. Okay. Most of the things we think of as cylinders do have that property. And by the way, most of the rulings we don't think of as being at a slant, like with the XY plane or whatever. We think of the rulings as being kind of perpendicular to the XY plane, but we don't even have to do that. This is like a very loose definition of what a cylinder is. Okay? This is like the truly mathematical definition of cylinder. It's very general. Okay? Any other questions? Basically, a cylinder, if I start, if I'm walking on the surface of a cylinder, there's always a way that I could walk so that it's like I'm walking on a straight line. Does that make sense? So if I have a surface that it's not possible to do that on, then I'm not on a cylinder. Cylinders are built from parallel lines. That's like the definition of a cylinder. They're built from parallel lines that happen to pierce through the directrix curve. Okay? All right, any other questions about that? Yeah, that's cool. So that's just the same definition of cylinder right up there. So a couple of notes I want you to be aware of. We're only going to really be considering right cylinders. A right cylinder is all of the rulings are perpendicular to the directrix. Or all of the rulings are perpendicular to the plane in which the directrix lives. That's what it means to be right. Does that make sense? So if the directrix lives in the XY plane, then all of the rulings are perpendicular to the XY plane. Yes, that's what it means for a cylinder to be right. And ones whose lines are perpendicular to the plane containing the directrix. The equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the other two variables. Okay, so if I have a cylinder whose rulings are parallel to one of the coordinate axes, that means that for that axis, like the z-axis, for instance, that variable is free, kind of like the picture we had right here, yes? The equation for this is x squared plus y squared equals, right? The equation for this is x squared plus y squared equals a squared. Z is missing. And the way that plays out is that the rulings just end up being straight up and down parallel lines with the z-axis, yeah? So that's what's being said right here. The equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the other two variables. So what about x squared plus y squared equals 1? What would that look like? X squared plus y squared equals 1. Well, okay, my directrix is the circle centered at the origin of radius 1 in the xy plane. Okay. Okay, and then what would I have for the rulings? Be like this. Okay. So like if I were to slice through this thing at any height, I would just continue to get copies of the directrix circle, yes? The rulings are all parallel to the z-axis in that case. What about x squared plus z squared equal to 1? What about that? What about x squared plus z squared equal to 1? What would be the difference between the cylinder I just drew and that cylinder? X squared plus z squared equal 1. That would start with a circle in the xz plane of radius 1 centered at the origin. And what would be going right through the center of that cylinder? The y-axis. The y-axis would be going through the center of that cylinder, yeah? And all of the rulings would be parallel to the y-axis. Okay, all of the rulings would be parallel to the y-axis. The whole picture would kind of be tilted 90 degrees to the right from the one that we just did, yes? So you would take this guy and you would kind of put it around the y-axis instead, rotate it 90 degrees that way, okay? Any questions on that? I think I'm going to stop there. We'll talk about quadric surfaces tomorrow. But there's where we're going to start getting some analogs to our conic sections. That's it. (11.5), the one with the distance formulas, is the last section on the exam.